should I just turn this off?
Yeah, turn it.
I turn it off. There are a bunch of just very discrete things to be done, and you just think about that problem. Like this week's problem was making pistons, for example. You know, I didn't have to think about how am I going to make the distributor cap or the ignition system. I'm making pistons this week, so everything else is irrelevant. And that's what kind of makes it nice and allows you to continue with the project. Yada, yada, yada. I particularly want to thank my wife, Jane, who's given me some support here, because she has given me support and forbearance with this project in the basement, in the home workshop. And this, of course, has also led me to have kind of a nice workshop, something that I wanted to have. You know, when I was a kid growing up in England, you'd pick up these popular mechanics magazines and you'd see all these wonderful American workshops. You know, and I had a little Black & Decker electric grill or something. So it's nice now to be able to say that, you know, I have a milling machine and I have a nice lathe and I have an oven and I have all sorts of bits and pieces, and it's kind of fun. Okay, enough of that. Now, I think that's all I wanted to say there. So, this is the subject. I've tried to make most of the slides pictures and not words, but I'm afraid the first one comes up like this, so I'm sorry about this. But basically what I'm trying to do is build something which is faithful to the original design, but not in exquisite detail. There are compromises that one makes because you're building a smaller device, and I'm not that good a model engineer that I can build things exactly to the scale. So I take certain shortcuts and so forth to do that. What size would you build if you want to build a model? Well, you could build a half-size model, but that's getting pretty hairy. The quarter-size model is very difficult to build because the parts get very tiny. So it's interesting that all these people in America who I've seen have been building models tend to build 1/3 scale. It just seems to be the default scale. The appeal of this engine is that I don't know of any other 3rd scale Jaguar model engines being built. I mean, lots of Chevy engines and Ford engines being built, and they're great too. And there are a bunch of guys out in California who do a wonderful job building those things, and they've given me a lot of interest, a lot of support, and I'll show you something that they made for me during the course of this project. But still, only Jaguar is the only one I have been able to discover.
So if you're going to be faithful, now you have to find somebody to build
Now,
a 1/3.
I should warn you, my hearing is terrible, and for hard questions it's even harder.
If you're going to be faithful, then you're going to have to find somebody to build a 1/3 scale XK120 for you, because that's the way Jaguar did.
Well, that's true. That's true. It ain't going to be me. I'm actually, well, the plan is to have the engine on a test stand running with a dynamometer and instrumentation. That's the plan, not in a car instead. It all started with Dave Randall, who happens to have joined us from Texas here today. Dave Randall had a collection of engine parts which came into the possession of John Brady, and John and Tom.
At a damn good price, I might add.
Yeah. And John and Tom brought them to my house, and so I had these bits and pieces. So I started by dimensioning, drawing up, measuring the dimensions of the block, and taking that dimension, dividing everything by 3, and putting it into a CAD system. So a CAD system is the one that I use for the really holds everything together on the project. We all know what an engine looks like. This is for the model engineers when I talk to the Model Engineers Club. It's pretty straightforward. I don't need to go into that. Originally, of course, this is an idea of how it's likely to come out. The original we know about. The capacity of the engine is 210 cubic inches. The model that I'm making is not 1/3 of that because I'm using wet liners in the engine. And the reason I'm using wet liners in the engine is because I'm not sufficiently skilled as a casting maker to make cord castings, which I would have to do. So this is a wet liner engine, so it's proportionally small in its bore. The stroke is the same. My estimate for the power will be something like about, with any luck, 2 horsepower, but 5,000 RPM. The scale, it would be much higher than that. Might be like a 6 or 8 horsepower, but what happens is that when an engine gets smaller, it gets less thermally efficient because the volume goes down, but the surface area of the cylinder stays up, so your thermal efficiency falls very rapidly. The small engines are never as efficient as big engines, so that's my excuse. But with luck, I'll get a couple of horsepower at 5,000, and obviously a lot of noise. I started out by making the block, cylinder block, and this really illustrates how I went about it. I said, if I can make the cylinder block and make that work, then I'll continue with the project. But if I fall foul at that point, then I'll just bail out and go and do something else, make model airplanes or something. So I started by making a wooden pattern of the block. This is a 1/3 scale of a block, but as you can see, it's just a chunk like that. It doesn't have any of the cutouts in it, and it will be cast as this block, and indeed it was. Similarly, the head was done the same way. And what happens is that what I did was I took this and then machined it all out, machined it away till it looked something like an engine, and you'll see the pictures of that. That's the block that comes from. I didn't do the casting, by the way. There's a very good casting company in Burlington, Mass, who only works in this aluminum, and he's a great guy. He's a good price, and more than that, he's interested in my project. And you know that's worth a hell of a lot. So here we have a picture of what the inside of the block will look like. You can see it's got 3 wet liners, there'll be 3 more in there. This is a section view of it, all done on the CAD system. And this is a view of what the thing is like on the outside. Here's a picture of what you see. This gives you an idea of the power of the CAD system. You can look at the whole thing, you can cogitate. And the nice thing about it is that when you drill holes at strange angles, they actually come out where you want them to come out. You know, it's just, it gives you power. Now you'll see there that it's like an open design. There's a large open cavity in the cooling cavity, which was done by drilling holes down from the back. Can't stop this really. But anyway, holes get drilled in from the back in there and make a deep rectangular recess. Okay, next slide. What you do is you take this 3D model in the CAD system, which has got all the dimensions in it, and then you select what you want to machine. You make a 2D drawing of it as you go down to your milling machine. So this is just happens an example of the drawing that I made. And the drawing only has all the dimensions I want at that particular time. And if I want to then go and do another part of the design or the block, I can go back and then make another drawing, and it dimensions itself up, and I'm away to go. So I don't have a drawing that's completely inundated with dimensions. It only has all the dimensions I want for that particular day. So it keeps you straight. And honestly, without a CAD system here, I wouldn't be doing this project. I'm not that smart a guy to be able to do it without a CAD system, but a lot of people could. This is a view of some machining that goes on. You can see here I'm milling in the pockets in the crankcase. I'm facing the bottom of the block there, and I'm line boring the main bearings there. This is what it looked like at 95% finished. Again, you can see that deep rectangular core down there. That was a fun thing to make. But I used a square drill for that. The cylinder liners, this is how I did the liners. It's a steel line. This is aluminum, of course, all this. It's a steel liner that sits in with an interference fit at the top and an O-ring at the bottom there. And that's basically how it's done. It's nothing very revolutionary. But the top is where it will be clamped here by a head gasket that will clamp that point, and that will hold it tight there, and then it will allow expansion to take place at the bottom. This is a normal way that many engines are done. There's no rocket science in that.
Did you think of cast iron?
This is made actually of 12L14. I didn't make it of cast iron. I used 12L14, which is a high lead steel.
It's got
I did think about cast iron and using centrifugally cast iron to do that, but I don't remember the decision. It was a couple of years ago, but obviously it was a good one at the time. I did pay particular attention to hone the liners. When they're in, I got this spiral flex honing thing, which is, in case anybody hasn't seen these before, these are really good. But they're dimensioned exactly to the bore that you want. So this happens to be a 9375, just under an inch bore, and you get a honing tool for that. and it spreads out, and that's the glue you use for it. And then once I've done the honing, I do a very light face across the top because these liners projected above the deck. And I wanted to clamp on each of those liners. This is the cylinder head, again the same story. It was a large chunk of cast iron, which was then cut, and it's not like a regular cylinder head, it's like an open deck design here. So this is all open, where on a full-size engine you'd have a full deck there. And again, this is because I was not able to make chord passages. If you look at a section through, I made the ports by using a ball mill that came in this direction, another one that came in like that. So I got an approximation of the shape of the induction tract, and similarly the exhaust tract as well. Again, this is the wood that we have over there, and this happens to be the metal. Again, pictures of machining. Perhaps what I should pass around here while I'm doing this is one of the frustrating times I had doing this project was when I got really stuck and I needed something else to do. I stopped it, so I built a 3D printer. So these are some 3D printing parts that I made. This is the half size of this block. You can pass this around and look at it. And this is the cylinder head. Again, you can pass that around and look at it. Those are not fine examples of the 3D printing technique, but they give you an idea of what's involved. So just pass them around as you wish. And there are other pieces up here to look at perhaps later. This just shows a setup where I'm tuning I'm getting the machining right so that I can bore the valve guides correctly. This is a finished cylinder head. Perhaps at the end of the day we may take the cylinder head off here and you can see inside it. It's not a long job to take. It's longer to put it together. Putting the timing chain together is not trivial, but getting it off is quite easy. Little spark plug. People say, where'd you get the plug from? Well, you buy it. There's a world out there. This is a 6mm diameter. This is a 1040 thread, so it's only a 3/16 diameter thread. And that is really essentially to scale for what we have in our engines. The crankshaft is made out of solid, and I'll show you quickly how I did that. It duplicates the features and the counterweights and so on of the full-size engine. You start out with a chunk of a bar, and you mill slots in it on a milling machine, and then you rotate it, say 30 degrees, and you mill another set of slots. So you can see the slots here. Now, if I go to the next picture, this is what I had hanging on the milling machine while I was doing the job. So you can see how because I need to keep track of one thing. I mean, one slip and you've scrapped the thing. So you see, in each 30-degree increment, I would take a series of cuts across at the appropriate depths. And gradually, by the time I'd done the whole lot, I'd end up something that looks like a rough crankshaft.
So how many crankshafts did you scrap?
None.
None.
None. And no cylinder blocks either, because believe me, you get real careful. On the other hand, I built 2 sets of connecting rods and 2 sets of pistons. But no, I didn't. The crank took about 200 hours, I reckon, to make. That's just machine time.
Now, do you case harden the crankshaft?
No, I don't need to do that. The reason is that it uses a steel of a sufficient hardness that you can. Let me back up. Charles Taylor of MIT has this wonderful book, and he's dead now, but he has this wonderful series of books on internal combustion engine design, and it's a Bible. Charles Fayette Taylor, 2 volumes, and what he says is that providing you have an adequate ratio of hardness between the bearing and the crankshaft of some number, which is like about 10 in Brinell numbers or something, that means that you're okay. So I meet the requirement. I don't have to go to a hardened crankshaft in this case. Had I wanted to, this is a self-hardening stainless steel, but I didn't take it that far because I didn't want to heat it and distort it too much. So I'm not running hardened, but I satisfied myself at the time that it met the requirements for what I needed to do. So I didn't harden it deliberately. Try and avoid that if I can, because of distortion and so on.
Right.
Okay, where are we? Okay, so now what we're doing is that we've sort of milled most of it, and then I have this device here which is like a rotating head, and here's the piece to be worked. And what I'm doing is I'm shaping the crank webs. I'm shaping those shapes here like this, and also these radii here. Do as much as you can on the milling machine before you go over to the lathe, because the mill has got more strength to it and more robustness. It's a good old Bridgeport lathe. This is turning the main bearing on the crankshaft. For those who are into these things, I'm using a rotating, a live center with a tailstock. I'm not using a center at the back. The reason being that if you have a center at the back and you push at the front, if you push like that, you're going to tend to bow the crankshaft when you're machining it. But if you're smart and you use a four-jaw chuck at the back end, then you don't have that bending moment and you hold things where it wants to be. Here's another tricky thing. You've got to make holes to get the oil through here, and this is really something that's quite difficult. You see the diameter of the hole. This hole is 0.078 diameter by 1.35 long, and it's this hole here that runs up here. And you've got to be so bloody careful because you can scrap the crankshaft if you break the drill off. So what you do here, what I did here, which is the right thing to do, is you drill the long hole first. You drill it blind because the CAD system tells you how far you have to go, and then you stop. And then you stop, you take the drill out, you breathe, and then you, and then you drill the cross drills, because if they break, you can pick them out anyway, they're very short. So always drill the long hole, because it's the breakthrough that's going to break the drill every time. So that's what I did with that. Oh, I used nicely expensive cobalt drills. But, you know, you need them sometimes. You can't get by with true value sometimes.
How did you start the hole at an angle like that without skidding?
I beg your pardon?
How did you start the hole at an angle like that?
Because I put a spot face, I did a spot face first of all. Good question. Very carefully, I did a spot face, so I made them. I don't know what size it was now. But once I did a spot face, then I do a center drill, and then I can drill.
And how did you get over stainless hardening? With lube or with picking the right?
How did I what?
Get over the stainless work hardening. That's a stainless crank, wasn't it?
It's 17.4 pH, which is, if you're familiar with precipitate hardened steel. I'm not sure that I did, because when I was attempting to make some connecting rods out of this material, I had a devil of a time drilling a hole through the middle of the connecting rod. And in fact, I never got success, and I would do about 3 of them, and then the drills would break and I'd scrap the part. And frankly, the only use that I had of those connecting rods was used as a key ring, on my key ring, because I gave up on these connecting rods. So, but this is one where I did get a hole all the way through, but I screwed it up in another way. Okay, and here you can see the crazy setup to do these angles. How am I doing on time?
Good.
Okay? Okay. Okay, so it ended up, because of all these efforts, I only had an eccentricity of about 2 mils, which really wasn't bad, I thought. But nevertheless, because I ultimately wanted to see that it turned freely in the main bearings, I wanted to reduce that run out. Line bearing and stuff like that, we don't need to talk about that. This is reaming the main bearings with an expanding reamer. Go into that. This is what we've ended up with now. We have phosphor bronze bearings, not white metal bearings. Phosphor bronze bearings at all the running surfaces here. The bearing caps have all got pins in them so that they're uniquely identified with a particular cap. They're all identified that way. And the running clearance is about 2 to 3 mils, I would say. Maybe a little large, but you know, you want the thing to turn freely. So here's it turning freely. And if I'd left it with the 2 mil bow, I wouldn't have been able to spin it like that. Even though that deflection is easily overcome by the forces of the running engine. The crankshaft, this is an interesting thing. 2 crankshafts. I start out by making a long hole up the middle, and then now this is this is a program, an example of modern technology. Okay, let me just show you what it does before it does. What you do is you build yourself an analytical model, the shape of a cam, and you model the piston, you model the valve, and you put a spring there and a damper there, because you've got to have that. And what you do when you run this, and you'll see it running, is that it plots out the displacement history versus time, and the velocity and the acceleration, and the peak torque required to operate the camshaft. Okay, John, see if it'll do it. It's not working now, but you can see what really happens is it's tracing out a little dot. You can see a little dot just tracing out there as it's going along, all right? So once you've done that, the real thing I was aiming for is how much force do I need? How much torque do I need on the camshaft? That's the big thing. Okay. And the reason for that is, well, I don't talk about it in the slides. I have a duplex chain system here, but really it's not a duplex chain, it's two individual chains, and only one of those is going to do the job. So I need to make sure that I'm not overdriving that single chain, and indeed I'm not. I'm in good shape. But that was why I did that. I wanted to know what the... Now, I could have done it with the back of the envelope and arm waving and everything else, but this is not fun.
Excuse me, why do you say it's a duplex chain but only one of them is doing the job? It's because it's two separate chains and you assume that one is loaded and the other one is a bit slack?
Yeah, one is going along for the cosmetic, because if I only had one chain on there, everybody would say to me, why do you have a double chain on that? It's not there for any other reason. Now, I don't necessarily know which chain is driving at any particular moment, but you can be sure that only one of them is.
Honda 750s, early Honda 754s have the same thing too, between the crankshaft and the input shaft of the gearbox. Two completely separate chains, and I always wonder, and there's no tensioner or anything.
No, unless you have some compliance between the two. I mean, if you have a spring system, that will load them up, but if they're rigid, no, it's a redundant system. It's not going to work. Okay. Okay, now John Brady and Tom lent me some camshafts, and what I did is I measured the profile of the camshaft. So at each angle of the camshaft, I measured the height of the tangent. So I have a table of angle versus tangent height, and this is how I use to duplicate the cam on the model. So I'm not asking you to read these numbers, but what I'm saying is I have this table which gives me angle, these are handle turns on the dividing head, and this is the height above the center line. So I've got that number, and then I can go ahead and, I know it's hard to see, but down here, at each rotary angle of this workpiece, I make a slice across. And I didn't make too many camshafts either. I was careful on this. So I was able to make the camshafts that way. So I made the cam profiles, and of course it wasn't a curve, it was a series of facets, but fairly closely spaced. So you can see there, you can see a cam profile, and then I'm now going to machine this lot away on the lathe. I wanted to keep this in place because that adds to the rigidity of the workpiece while I'm machining the cam. And then finally, this is what the cam looks like in the lathe when I'm doing the finished turning. Here I'm reaming the camshaft bores. I'm using plain aluminum here. I don't have any lines in here. I think I can get away with that without a problem. I couldn't make. I didn't have a long reamer. First of all, because you can't run out of the end here anyway. So this is a short reamer, but luckily it seemed to work out fairly well. Now this is the cam installed in the head with the timing sprocket on there. This is a view of the engine. Again, this is a check drawing, and again, once again, you can see how it assembles. You can make sure you don't have any interferences, and you're also on the CAD program itself. You can obviously rotate the crankshaft, and you can see things moving, and you'll see evidence of that. Here's something you've got to worry about. Is the connecting rod going to hit the crankcase or the bottom of the liners? So again, you know, I could find out that in fact it does clear. Well, I had to do some additional machining out when I looked at that. This is the other thing you need to learn about when you do these CAD things. And I've been caught this so many times. you've got this drawing here and you're working away at it and you think, oh geez, I don't know, I should take a little bit more out of this or something. Fatal. Do not design on the fly. Go back to the computer and check the drawing, because that's how things get scrapped. I've done it, I know, ask me how I know. In this particular case, only this week, I was trying to put the pistons in, and I moved I had the connecting rod disconnected here, and it was resting up in this cavity here, so that the wrist pin was sticking above the top of the block, and I could throw the wrist pin in, pop the piston in. Well, it wouldn't go. And it wouldn't go because I had not really accounted for the radial clearance. This is a square end and this was a radius, and I did a little bit of gentle filing and rounding of the corner, and then I could get the engine together. But it was almost a showstopper. It was embarrassing if I couldn't put the piston in. Okay, this is again, this is another view which should run by itself, but it doesn't. Oh, this is supposed to be. This is kind of cute. Could you do the honors? It shows the engine coming apart. It's not running. Okay. Well, never mind. We'll move on from that. Oh, it's a shame. Here's an interesting thing. Making the gears at the front of the crankshaft. You have to make a worm. It's a seven-start worm gear, and it runs on a 14-tooth helical, which drives the distributor and the oil pump. And that's really quite a tricky thing to make, particularly the 7-start worm. This is not a catalog item. So I ended up making this, putting a rig together where I modified my Bridgeport with a right-angle gearbox and a drive, and there's a 5-to-1 worm box, and here's the worm blank and the cutter. So it's basically, and I've got a picture of it running, which it may run here. Now you can see what's the table is moving. This is rotating the workpiece, and there's the cutter cutting the gear. So there's a lot of geometry involved in that, getting that right again, which I won't bore you with. And that's why I made an aluminum to start with, to make sure that it was working right. And then I went ahead and made a bronze one. This was actually made on a professional Barber Coleman gear from a friend of mine in England. This Barber Coleman was supplied to England by the United States in World War II. And he bought it from Rolls-Royce as surplus equipment for like £50 or something. And it's great. I mean, it really is a beautiful bit of machinery. So that was good. And this shows the gear assembled inside the engine. The original timing chain arrangement we know about, and this is a duplicate of that. It uses, as I said, 2 single chains on each, the upper and the lower half. These are the smallest industrial grade drive chains you can buy. So they're not exactly to scale. They're about 20% bigger than scale, but they're close enough for government work. And they cost about the same as gold jewelry chain. I don't have any left over to give
That was
you.
the grocery money, was it?
Okay, now we need an oil pump. Well, making an oil pump, this is called a Geroda pump. It has a rotary, a 4-lobe rotary, and then a 5 recess outer piece that rotates eccentrically. And this is how it moves oil from one side to the other, by this rotating and so on. Very difficult to make this, because you've got to keep it very, very close clearances so that it doesn't leak. On the other hand, the slightest error, you can see here, it's going to seize up. So I found a Honda motorcycle pump that would do the job. So it was easy to buy a Honda motorcycle pump and build the rest of it around that. Won't bore you with this, but this is another nice tool that's available, which allows you to design the pump and check its capacity and flow rate and so on and so forth. So that was another fun thing. These are the oil pump components. These pieces I bought from Honda. Everything else I made, the porting and all the other bits and pieces. This is what it looks like, mounted on the front bearing cap, which is where it normally sits. You can see the 4 and the 5 pieces here. And that's the cover taken off, so you can see the porting on This is this week's project, making the pistons, a second set of pistons. They're made from solid bar. It's a high silicon aluminum which has low wear and also low expansion coefficient. And it's fully machined from bar, so there's a recess machined up inside here. I've tried to give some uniformity to the area underneath the piston ground by doing that. The piston rings, these are great. I didn't make these. There's this guy, Dwight Giles, in California, and he wrote this article in a model engineering magazine. He says, this is how you make piston rings. And he had all these beautiful gadgets. And these rings, I didn't bring any today because they're too bloody valuable. But, but they're absolutely beautiful. They've got little slots in them and everything. And so I just called him up and I said, hey, Dwight, you want to make me some rings? So for $100, really, I got 2 more sets as well. I got enough for 8 pistons, and I got all the compression rings and all the control rings. I haven't checked them for gap yet. They're not on the pistons, but I mean obviously the pistons take them. Yeah.
What is your design compression?
8-to-1 volume. They do. I must admit, I'm looking at this piston crown here, and I'm looking at what Brian Donovan had up, you know, and I'm thinking, God, that doesn't look very high, that crown. Maybe I need to go back to the drawing board. But at least if I have to reduce them, I can. I've got some material I can take out if I need to. So I need to double check on that, or maybe put a thick head gasket in. Okay.
Well, you could also measure it. You could, once you get it in there, you could measure.
Yeah. Oh yeah. Yeah. This is right now. I'm just using the computer to tell me. The CAD system will tell me. See, it tells me the volumes and everything. You don't have to think. You just have to push the button. But you have to know what sort of answer to expect. Otherwise, you could be led astray.
Well, you've got a smaller bore, you were saying, which is why you've had to go to a higher crown. Because you've got the chamber in proportion and your bore smaller.
Yeah.
Your swept volume versus your chamber volume is going to be smaller.
Yes, I mean, I did the arithmetic. I don't remember now, but I did the arithmetic at the time. Yeah. I know what the swept volume is and so forth. So. Okay, this is the flywheel at the back, and this shows me machining the teeth on the flywheel. 85 teeth on the flywheel, and that messes with an 11-tooth starter pinion. And here's an interesting thing. If you're just designing a gear train, and those of us who've done this, you have a concept of diametral pitch, which says you have a certain number of teeth for every inch of diameter. It's a diametral pitch. And if you do that on the sort of spacing for this engine, you would end up with 12 teeth on the starter pinion, not 11, because that's what the diametral pitch would tell you. But if you go into the ASME books, there's a whole section on starter drives, and it's very interesting because I just found it by accident. What you do is that you calculate that, say, for 12-tooth spacing, so you would space it out for 12 teeth, and you only put 11 teeth on. So you have some extra leeway or wiggle room to get your pinion to engage. See, often it only has to be agricultural fit, because it's only going to be there for a short time and whipped out again. It's not going to run all the time. So you need to get freedom of engagement and disengagement, which then leads to the next picture. Okay, before we get there, this is the starter, which you can see on the side of the engine. I tried to get one of about the correct scale diameter. This is a very, very fine motor. It's made in Germany. It's a very high torque motor. It has a stall torque of 12 volts of 10 pound-inches. And it's only that big. It's brutally efficient. And at 4,500 RPM, I'm getting a tenth of a horsepower out of it. So that's this. It has a hardened shaft coming out. I need to make a one-way drive here. Of course, you've got to have a one-way drive on your starter drive. But the way I've done it is I cheated. I used a one-way clutch, which I stuck into the pinion. And I thought, well, I've got to try this because otherwise making a one-way clutch is beyond my capability. Well, it does work, actually. It's really rather good, I must say. And then these are some springs that are needed. You have a spring to disengage the pinion and another spring that helps the engagement. Okay, so here's a picture.
So that's your crash or something like that, right?
Say again?
It's a crash code.
Yeah.
Yeah.
No, it's not. It's not. It doesn't start to turn. The pinion does not start to turn until it's engaged, because there's a micro switch at the back here. Okay. Okay. So we've got what this is the first test, and this is a test where you want to make sure that the thing will freewheel. You know, when the flywheel, when the engine accelerates, you want to make sure it comes out of engagement. So that's what that was showing there. Now the other thing that you've got to make sure is, can I generate the torque to turn the engine over? So I calculated the torque required to crank the engine, and I made up a winding drum, which I put on a, we'll run this again, honey. Okay, what you'll see here is very quickly, there's a winding drum, there's a meter, there's a weight pad, there's a fishing line. Anyway, it really made me laugh. But there's the load pail, there's the line, the pulley, and there's the fishing line to the winding drum. And that's the meter, a good old-fashioned analog meter, which you need sometimes. So that was my starter motor drive run test. So that seems to work. And this is the short block assembly, and if you want, we can take the cylinder head off and look at that. I use rubber bands to hold these together. I really need to do something better than this, because it's really fiddly putting it together. The back side of the engine, because I'd made a rectangular hole for the water cooling passage, I needed to cover that up, but I also needed to be able to drain oil from the valve, from the cam areas. So these are oil holes that come down from the cam cavity, and then they mate up with these holes here that run down here, one on each side, and those holes pick up holes at the bottom of the block that squirt down into the oil, squirt down into the crankcase. I mean, I'm a little worried about whether it's going to jam up or it's going to work or not, but that's the present design. So this is the build status today, which you're looking at here. Take the bottom off and you can see the cranks and the oil pump, and there's the machine sump that was machined out of a solid chunk. And just some references here, and particularly I want to thank the Brady brothers for the loan of the engine components. And there are various references here that may or may not be of interest. That's the show.
All right, we want to thank Bruce for that. That was great. Would you like to come up and take a look at the actual model? Right here.
Somebody's glasses are up here on the.
Whatever happened to my little pieces of my plastic?
Here,
Oh, you've got them, have you? Okay.
I have one of them.
Thank you very much. We'll see you tomorrow.
There we are.
I mean, just so you know, honey, what are you
Just give me one thing that I can hold on to believe in this living such a heartbreak call. So Lord, you made me an angel, flies from the government. You made me a poster of an old rodeo. Just give me one thing that I can hold on to believe in this living such a heartbreak call. Lord, to believe in this living such a way to go. I kind of renegated that song. I took up on the guys and they're kind of going, what? What you doing? I'll throw a little Joni Mitchell out there for you.
How are you?
Squeezing by you, hon. We're going to do one more song in the set. We're going to take a break and come back. We're going to take a short break. We're going to come back. We're going to talk about Hackensack and a few other things. I'd actually never heard of Hackensack before. And now we do two songs that both have Hackensack in it. It's amazing.
Here, tell me what you think and what you want me to do.
I think you're ready to go. Come here. I used to know you when you were gone. You were in all my dreams. Thank you. So that was the first song introduced to me where I heard, now I know about hacky sack. When I was first singing the song, I kept singing hacky sack, and my son kept saying, Mom, please don't sing. Really happy to have Dan back up with us.
Thank you, very nice.
Do a bye-bye tune.
All right, you get that water.
Down near the river, there's a sea. I don't know why I love you like I do. After all the changes you stole my money and my cigarettes. I ain't seen the worst of it yet. I wanna know, oh, won't you tell me how can I stay here with you? Oh, take me to the river. Wash me down, take me to the river again. Back on the ground. I don't know why it's so bad. After all the good times that we had, we're sitting candles and burn on the wall. Now who's the biggest fool of us all? I wanna know. Oh, won't you tell me how can I stay here with you? Oh, the river, wash me down, take me to the river again, back on the ground, yeah. Oh, love, and you can tease me till I can't take damn fancy. I don't know why I love you like I do. After all the changes that you went through, love is a notion that I can't forget. My sweet 16, I would never regret. I want you to tell me how can I stay here with you? The river, wash me down, take me to the river again. Oh, take me to the river, wash me down, take me to the river again. Back on the ground.
Of 4 tech sessions that we're having here at the 2014 AGM. My name is Carl Hansen, and John Brady, John and I, the co-organizers of the tech sessions. And thank you very much for coming. You're filling the room. We're going to need some more chairs. I'm going to make this introduction very short, except that this is the first. At 4 o'clock, we have Bruce Murray talking about the construction of a